Hello, Math 1224. This is Dr. P with Lesson Launch 602, Letting It All Hang Out. Take a look at this integral here. You'll notice there is something funny going on here. There is an infinity symbol there. So this is an integral in which we are integrating from 2 to infinity, whatever that means. Now that again is an example of something called an improper integral. Improper because either one of my limits of integration or the function itself goes to infinity somewhere. All right, now in this particular case, I'm working with a function 1 over x cubed, which is reasonably well behaved on the interval I'm looking at. I'm looking at the interval from 2 to infinity. This function does run into trouble at x equals 0, but that's not in the interval that we are considering right now. However, one of the limits of integration is infinity, so for that reason, this is an improper integral. Now, we always think about improper integrals as limits. This is a limit of proper integrals. In this particular case, we're going to think of the integral from 2 to infinity of dx over x cubed as the limit as b goes to infinity of the proper integral from 2 to b of dx over x cubed. Okay, so all we're doing here is we're analyzing this infinite integral, which may or may not have an infinite value, but it's over an infinite interval. We're thinking of this as the limit of proper integrals as we let this right-hand limit of integration go to infinity. Now we do this because the thing on the right is something that I know how to evaluate. I know how to evaluate a definite proper integral, and I know how to take limits. So I'm just going to go ahead and evaluate what I see there. I'm going to say that's the limit as b goes to infinity of, now let's see, what's the derivative, or well, the antiderivative of that? I'm going to go ahead and do one more step here, which is to write that as x to the minus 3 dx. And then that helps me to see how to take the antiderivative. That's, that's 1 over negative 2 x to the minus 2 from 2 to b. So let's go ahead and evaluate what that is. That's going to be, I'm going to leave the limit there for now, not evaluate it just yet. But that's going to be, let's see, I've got negative 1/2 times b to the minus 2 minus negative 1/2 times 2 to the minus 2. And then that's going to be the limit as b goes to infinity of, I'm just going to simplify a bit here. I see that this term is going to wind up being positive, so I think I'll just go ahead and put that first. That's going to be, let's see, negative 1/2 times, that's really 1/4 there, so that's going to be 1/8 minus 1 over 2 b squared. And then I just think about what that does as b goes to infinity. Well, this just remains constant at 1/8, and as b gets really, really big, this denominator gets huge, so this fraction's value goes to 0. So I should get just 1/8 as the limit. So what that means, conclusion, is that the integral from 2 to infinity of dx over x cubed is 1/8. So what this is saying is that if we were to just integrate this function as far out as we wanted to, the value of that integral would get increasingly close to 1/8. It would never surpass 1/8, but it will get as close as we like. So we say that the integral from 2 all the way out, all the way to infinity, is just 1/8. Now, one thing I've been a little bit dishonest about so far, let me just zoom out on this so we can see the whole thing. So this is an example. All of this was an example in which an improper integral has a finite real value. because this limit we calculated exists. And in the previous video, we calculated another improper integral. We didn't quite call it that at the time, but that was another improper integral that has a finite real value. But, and this is very important to understand, this doesn't have to happen. This does not have to happen. So to give another example, let's just move out of here for a minute. Okay, so here's another example. Suppose I give the integral, or ask you about the integral, let's say 2 to infinity again, of dx over the square root of x. And let's see what happens if we evaluate that in the same way. All right? So we're going to evaluate this by viewing this integral as a limit of proper integrals. Limit as b goes to infinity of integral from 2 to b of dx over square root of x. And that's the limit as b goes to infinity of integral from 2 to b of x to the minus 1/2 dx. And then using the power rule, that's the limit as b goes to infinity of, let's see here, I believe that's going to be 1 over 1/2 x to the 1/2 evaluated at 2 and b. I don't know why I chose the constant 2 in it. So that lower limit of integration was just a free choice on my part. I just picked that for the purposes of this example. And now I'm kind of regretting choosing 2 because there are so many dang 2's in this problem and in the previous one. But anyway, this is the limit as b goes to infinity of, let's see, that's just 2 square root of x. So I think I'm going to get 2 square root of b minus 2 square root of 2 if I'm doing my calculations correctly there. There we go, that's a b. Now think about what that does as b goes to infinity, this expression here. This just remains minus 2 square root of 2, nothing magical there. But what about 2 square root of b? Well, when you think about b getting really, really big, now the square root of a number, taking the square root of a large number makes it smaller. But still, as b gets really huge, this square root is going to get as big as we want. There's no upper limit on how big the square root of b can get. So that means that this limit is going to approach infinity. And usually I don't say that the limit exists in this case. I don't say the limit exists in this infinity. Instead, I say the limit doesn't exist, but it approaches infinity. Now, I want to just step back here and think for a minute about what this means and be really clear about that. So what that is saying is that if I were to take this integral and chop off some proper finite piece of it here, so let me just put that in a different color there. So let's say I just chop off this piece, the piece from 2 to b. I can evaluate this. This will have a finite value. The part in the blue rectangle will have a finite value for a fixed value of b. I want to be really clear about that, if b is fixed. But if we let b grow, that finite value can get as big as we want. So if I wanted to find some region over which the integral of this function is, say, 1,000,000, I could find it. I would just need to specify the right value of b. If I wanted to make that area 1,000,000,000,000, I could do it. I just need to make b big enough. There's no upper limit on what the value of that can be, which means I can't pin this number down here, which is not really a number at all. I can't pin this integral down and assign it some finite value. There's no finite value big enough. So for that reason, we say that this integral, this improper integral, this one, is divergent. Okay, not like the teen novels by Veronica Roth. Divergent meaning that this has no finite real value. Whereas on the other hand, the integral we worked with here, we said that that one, or we would say that this one is convergent. Convergent. Meaning it converges to a finite value even though we're integrating over an infinite interval. So anyway, those were examples of convergent and divergent improper integrals. And the thing that I find students always have kind of a hard time getting their heads around, and I don't blame them, this is actually a very hard idea to get your head around, is that something like this integral from 2 to infinity of dx over x cubed, that can have a finite value, but something that looks very similar to it, this integral of dx over square root of x, has an infinite value. After all, both of these functions, if you let x go to infinity, both functions go to 0. Both of these functions go to 0 if you think point-wise. And yet, nonetheless, this integral here, this area from x equals 2 to infinity, this area has a finite value. It's just 1/8. Yet this integral here has no finite value. And the short story about why that's true is that this function here, 1 over x cubed, converges to 0 very, very fast. It converges to 0 so fast that it's just not going to add on enough area to grow without bound. And on the other hand, this function here, it converges to 0, but it doesn't converge to 0 that fast. It kind of takes its sweet time. And because of that, if you let this limit of integration go out adequately far, you can make this area as big as you want to make it, or rather I should say this area. You can make this area as big as you like. So anyway, that is an introduction to integrals as x goes to infinity. In the next video we'll talk about what happens if the function has a discontinuity and the function value goes to infinity. That's it for now.